Hello, good afternoon everyone. It's really great to be here at Scale by the Bay, our first time at this conference. So today we're going to be talking about deploying end-to-end machine learning pipelines with Apache Spark, Kubernetes, Kafka, and the Model Asset Exchange. So first, a little bit about us. This is my colleague Prashant.
Hi. Hi. So, both of us are part of IBM CODAIT group, which is Center for Open Source and Data and AI Technologies. We are Spark committers and PMC members. My interest area is Spark structured streaming and Spark on Kubernetes.
And I'm Nick Pentreath, ML Nick on Twitter and GitHub. Also at the Center for Open Source Data and AI Technologies, focusing on machine learning and AI frameworks and open source projects. Author of Machine Learning with Spark, a book a little bit out of date now, but hopefully one of these days it'll be updated. So before we get going, a little bit about CODAIT. We're an open source team within IBM, over 30 open source developers, and our mission is to enhance the state of the end-to-end enterprise AI lifecycle out in open source. So when I joined the team a few years ago, it was mostly focused on Apache Spark. And since then, the focus has really expanded to include the rest of the Python data science stack, deep learning, model and data exchanges, which we'll be talking about a little bit today, as well as projects for AI fairness and explainability and model deployment, open standards and frameworks for serving. So we'll start today talking about the machine learning workflow. And the common perception is, you just throw data at machine learning and you get out profit, right? You're done. But this workflow is a lot more complex, right? So it spans teams and silos. It starts with data, which is sitting around in various locations. Some of it is historical, some of it's arriving in real time. Streaming is what we'll kind of be talking about today. And that's the provenance of your data engineering teams. Then the data scientists and researchers are taking that data, ingesting it into their workflows, doing data visualization, exploration, taking the data that is in raw format and transforming it into a form that can be consumed by a machine learning model. That's data transformation, feature extraction, feature pre-processing and engineering. And then that little piece in the middle of model training, which is what all the data scientists and researchers really want to do. It's quite a small piece, but important. Selecting the best models, testing it on data, doing the evaluation and figuring out what is the best approach for a particular data set and problem. And that's where a lot of the discussion often stops, but there's no point in having a machine learning model that's trained on data unless you're actually going to make predictions in the real world. So the next phase is deployment and actually throwing it over the wall from these data science and research teams into your machine learning and production engineering teams and getting it to deploy it into a live system, actually predicting on new data where it has to be monitored. And most of the time you have a feedback loop. So the model itself is generating new data, its performance is changing over time, and you have this kind of feedback loop back to the beginning, that data and ingest phase. And that's, again, the provenance of your machine learning production engineers. The workflow also spans many, many different tools, a whole zoo of tools. And it's a small but really important piece of the whole puzzle. So this is by now quite an old diagram from an old paper by Google, the hidden technical debt in machine learning systems. But I really like it because it illustrates that that entire workflow is only, perhaps 5% of the entire problem. And really what we have to worry about is interfacing this machine learning piece with all of the other different pieces. In particular, for deployment of machine learning models, the serving infrastructure, the monitoring, the analysis tools, the streaming systems, and so on. So before we talk about the streaming side, we'll just talk about this model deployment phase. And when we talk about model deployment, we have to answer three questions: the what, the where, and the how. So what are we deploying? What do we mean by a model? Where are we deploying it? Is it a batch environment, streaming, real time? Are we making real-time predictions in support of a web service, batch scoring, a bunch of data, and how are we deploying it? What is the actual DevOps mechanism? How are we actually getting it into production? What is the software deployment mechanism? So starting with the first one, what do we mean by a model? Now, we saw that machine learning workflow, most of the time we think, okay, once we've got a trained model, that is the model, right? It's an algorithm, it's a bunch of numbers which represent the weights of that trained model, and that's it, we're done. But if we go and look at that workflow that comes before the model training, we know that to take raw data, we can't just feed it into a machine learning model, it has to be transformed into a bunch of vectors, a bunch of numbers, and we need to take the raw data and apply feature transformations, extraction, pre-processing. Now, that's what we do at training phase, and if we do not do exactly the same steps at prediction phase, we get garbage in, garbage out. So that's known as train test time skew, and we need to ensure that the entire pipeline is the same at prediction time. And what we've always heard about deep learning is that it does away with this need for feature engineering, right? We just throw our picture, our image at our fancy neural network, and out comes the correct prediction, right? But in reality, again, a deep learning pipeline is a lot more complex. So yes, at the core inference phase is using our favorite framework, and it's our fancy deep neural network model, the latest and greatest from research. But before we can feed it into that framework that requires a tensor or a set of vectors, we need to pre-process the image, and then once we get the prediction out of that framework, we need to do post-processing. So the image pre-processing is typically done in deep learning land. It's in Python, OpenCV, TensorFlow, Pillow, and then even once we get the prediction out, we've got to do a lot of post-processing, which is typically custom code. So there's a lot going on here, which is a lot more than simply the core algorithm. So we need to think about deploying pipelines and not models. So one way of doing this is to think about using containers, and containers have become, rightfully so, a really popular way of deploying software. It gives you repeatability, ease of configuration. In particular for this application, we have the separation of concerns. So data scientists can worry about the what. They can use their favorite framework, they can train in TensorFlow, whatever they want to do, and they don't have to worry about how that's going to get deployed. They just package it up as a container, throw it over the wall, and okay, your ops teams and machine learning engineering teams running production infrastructure can just deploy it. You get some stuff for free, monitoring and fault tolerance and so on. But that question about the what is still really important. So what goes in the container does matter because performance matters. So if you just throw arbitrary Python code in there, you don't know what the performance may or may not be, and you got SLAs to worry about. And it doesn't solve this problem of how you interface with that model. So once that microservice, let's say, that model has been deployed as a Docker container, how do you actually call it? How do you actually incorporate it into the rest of your application stack? So this is one problem that we're trying to solve within our team with a project called the Model Asset Exchange. So the steps that one needs to go through to actually find a machine learning model that works is you've got to go out there and see, is there an existing model that does what I need? So if I'm doing image classification, what is out there? Is it performant enough? Does it meet my use case? Can I actually use it from a licensing perspective? If a model exists out in research, then I need to go and find the code for either training or deploying that model. So is it out there in open source? A lot of it is research code. Is it actually production ready? Some of it may work or may not. Checking licensing. If I'm training the model, then obviously I've got to use all the different frameworks, worry about data licensing. And what we're really worried about today is deploying and consuming. So I've got to make any adjustments to that code, package it up, deploy it. And again, this requires a lot of time, expertise, and resources, and it doesn't necessarily solve that standardization problem. How do I know how to actually call this model? So in the Model Asset Exchange, it's a free and open source collection of deep learning models, sort of state-of-the-art deep learning models across various domains. So it's one place to come and find all of these models, a wide variety of domains. We go and test the code in the IP and ensure that it's open source licensed and that it all works for production use cases. And we have pre-trained versions of state-of-the-art models that can be deployed, as well as you can train them yourself. So we go through all of this, all of these steps. We're eliminating these barriers to entry that exist that we saw before. We've gone through all those steps already. we found the model, validated license terms, wrapped it up in our framework, and we provide a standardized REST API, publish it as a Docker image on Docker Hub, so it can be one-click deployed into a Kubernetes cluster, for example. So a deployable asset takes this data, model, compute, and expertise, puts it together with the processing and the compute power, of course, and you get a pre-trained model. But what's important here is that a deployable asset on the exchange is both the pre-processing and post-processing code that we saw before, as well as the model, and a standardized REST API. So you get something that is easy to use, and it speaks JSON, and you can easily incorporate it into your application. So as much as possible across different types of applications or use cases for the models, we standardize the way that it works. So you can kind of drop in, replace different Max models, and they all sort of speak the same API. So going back to that workflow, we saw that there's a lot of different steps, and Spark streaming and yes, the Spark ecosystem can really solve a lot of these problems. So for ingest, data processing, the feedback loop, we can use Spark streaming and message queues like Kafka. For model training, we can use whatever framework we want. And for deployment, we've seen that we can have a standardized container-based microservice that exposes a standardized REST API with the model asset exchange. So combining all of these different components, we get a really good solution. So Prashant will talk us through some of why we want to use some of the other components, Spark streaming, Kafka, and Kubernetes.
Yeah, thank you, Nick, for explaining how model asset exchange makes it easier to deploy machine learning models. Moving to why we need Kubernetes, Spark structured streaming, and Kafka. So Kubernetes is an open source system for container orchestration. It offers scaling, automatic deployment, management of containers applications, and it provides a lot of convenience features on top of that. Not going to the all the details of it. Why we chose Kubernetes? Because we can scale dynamically. We can just say change the replica counts from X to Y, and Kubernetes steers the ship to move and meet my requirements. I don't have to worry about load balancing. All services are load balanced. Decouples infrastructures and scaling, makes things easier for developers to deploy. Above all, Spark, you can use Kubernetes as a resource manager. So thanks to the Spark on Kubernetes effort, it makes deployment very easy. Spark can more intelligently scale itself. It can make a decision on how to elastic scale based on the amount of tasks pending and so on. And there is another advantage that since the entire system is running inside Kubernetes, there is no need to expose any service to external. This makes things both easier in terms of logistics and also in terms of isolation and security. So this is one downside. Kubernetes system is pretty complex, and this challenge comes when we are actually maintaining Kubernetes ourselves. But most likely, if I need a Kubernetes cluster, I'll go to Google Cloud or Amazon or somewhere. So I don't hit this problem in that case. But if I were to operate it myself, like while developing this demo for this talk, I was trying to set up my own Kubernetes, and I got to understand this. Next is Spark structure streaming. Given the popularity of Spark, it's already well known. It's a scalable, fault-tolerant stream processing engine built on Spark SQL. Lets us write very expressive code and concise, functional. And above all, it makes it, as I said, writing streaming job without having to reason about it. So the same code that can run a batch job can also run almost the same code can run the streaming analytics job. Makes it very easy to work with. So the entire data set in the batch case can be viewed as a table, and in a streaming case, it can be viewed as an unbounded table. So Kafka is well known for processing large volumes of data. It's distributed, fault tolerant, and Spark streaming plays really well with Kafka. It has a built-in connector for Kafka, and on top of it offers performance and reliability guarantees. So going forward, we built this demo for tweet stream sentiment analysis. We are using a Kafka message queue, and we are the stream itself is of popular airlines in America, and there is a machine learning model to process the sentiment, and Spark streaming does both, trying to simulate a stream for the demo and also perform analytics. We'll go into that. A bit about the data set. It's sourced from Kaggle. It's a 1 month of tweets on travelers. There's a sample, United and American and so on. And we are using the model asset exchange text sentiment classifier. Nick can briefly talk about that.
Thanks. So yeah, given that we're using an airline sentiment data set, we'll probably expect that there's going to be quite a lot of negative sentiment, but hopefully there'll be some positive stuff in there. So we saw before how the model asset exchange gives us a one-stop shop for various different use cases, and as it happens, on Max we have a text sentiment classifier. And for anyone who knows a little bit about the latest advances in natural language processing and deep learning, they'll know that a class of models called the transformer, and pre-training very large language models with these architectures is kind of the state of the art in terms of what you can do in NLP domain. So the text sentiment classifier is based on Google's BERT, which is effectively taking these state-of-the-art state-of-the-art transformer networks and pre-training them on a huge amount of data. And the idea is that you take all of this English language data, Wikipedia and kind of the whole internet, pretty much, and you train this model on tasks such as predicting the next character or predicting the next sentence based on what's gone before. And in a completely unsupervised manner, this results in a really big model that's really good at doing a bunch of stuff in natural language without necessarily having to tune it to a specific use case. But what you tend to do is then fine-tune it a little bit more. So for text sentiment, for example, it's a classification problem. It's tuned on an IBM dataset from the IBM Debater project, where they actually created a system that could debate against a human. And this is the claim stance dataset. So it's a bunch of small text annotated with whether it's a kind of positive or negative sentiment. And what's interesting here is that even though the model has been trained on something that's not tweets, and tweets and social media have a fairly specific distribution of words and lengths and the kind of language in there, and characters, for example. Even though it hasn't been trained on that particular data set, it actually transfers really well to performing pretty well on small data sets, tweet data sets. That may not be the case if you look at trying to do sentiment on very large, data sets like long movie reviews, for example. But in this case, it works pretty well. So the idea here, as we saw before, is that Max creates this really nice API. We just feed it JSON with the text, and we get back a JSON that specifies what is the predicted probability of being positive or negative. So here we see, Spark streaming is great. Well, that's a positive statement. And Flink is not my favorite framework is a negative statement. So it does a pretty decent job at kind of arbitrary text. Now, one point to note is if we're in a streaming environment, this kind of setup is good for real time, right? I mean, you give one input and you get one output. It sits behind an API. It's a microservice, so it could support a real-time application pretty nicely. If we were moving on to streaming, unless we kind of record at a time, we're in a mini-batch environment typically. And that's the case for Spark streaming, so unstructured streaming. So in this case, we may not care so much about latency. I mean, we still might be in the few hundred milliseconds latency or even a few seconds, but typically we're not hard real time, so we don't care that much about latency, but what we care about is throughput. So what we really want is to be able to batch things up a little bit. So fortunately for us, machine learning models in general do pretty well with batching. They're kind of designed to be trained on many batches of data. So at prediction time, you can actually speed things up and get a lot more throughput by doing batching. So if we put together a whole bunch of documents and feed that through to the model, fortunately we get a batch response. So this fits really nicely with our use case of doing predictions on mini batches within streaming. So we can now use this Max text sentiment classifier. It's already packaged up as a Docker container. Since we're running everything else on Kubernetes, we can just drop it in.
Thank you, Nick, for explaining how we can do model scoring or predictions using Max text sentiment classifier. The best part I like about it is that it exposes REST API. I don't have to worry about how to deploy the model or how to do, a lot of stuff that goes around inside it. So getting onto the steps that goes through in the entire streaming pipeline. First one, since this is a demo and I needed a stream to work with, so I have a Spark job which uses a rate source that lets me specify, how many rows per second I need to generate. So it's just a generating job. It randomly chooses from the data set we spoke about. It randomly chooses tweets and sends them to the Kafka service. Next, there's second Spark streaming job, which does the analytics and model scoring using Max text sentiment classifier, as we talk about. So, since these streams, these tweets are coming in real time, so as they come, for batch of tweets or each tweet, I make a service call to the text sentiment classifier service, gets the sentiment and perform the analytics and displays it. So this is the entire cycle that goes around. And the whole thing runs inside Kubernetes. So the best part about that is it makes scaling this very easy. So if I were to suppose increase the rate to 1 million rows per second, then all that Kubernetes has to do is increase the replica counts for the microservice in question and the number of executors for Spark. And the whole thing can scale seamlessly. We offer single-click deployment. You can to try this demo out, it's working demo, you can try it out. Clone the repo and just run this command. I have a brief video of the demo. Yeah. So after running that command, I check the pods that are created. So the first item happens to be the executor for data generating job, the Spark data generating job. And then there are 3 instances of the microservice that does model scoring from IBM, that Max text sentiment classifier service. And then there is Kafka and Zookeeper to do the message queue. And the Spark ML pipeline is the actual analytics job, this one. So you see the results. Since it's printing to the console, we just need to see the logs. Here we see, so here we see tweets and their corresponding sentiments. And there is also an overall aggregate of, so-and-so airline got so many positive reviews and so many negative reviews. So not going into the details of those. Next, if you like to try this out, I have this open sourced. Your contribution in the form of feedback is very much welcomed. A bit about what goes behind the scenes for this demo, and this is the simplest Spark job, which is like Spark Pi example. So if I were to do this, I just using the same demo repository I worked with, I would just specify the cluster configuration for Spark and say, deploy mode is cluster, and this is the class I wanted to run, and so on. And rest I leave it to the defaults. Then I say Spark job deploy via pod. This is very helpful because if you're working in a client mode and your system, your local laptop is behind the NAT or firewall, the workers cannot connect back to the laptop, the local machine, and that leads to all kinds of problems. So we deploy via a pod. I spin a pod that has a Spark image, and that pod deploys for does a Spark submit, which spawns further executors. And starting the job or cluster is as simple as saying .start, and then we can wait on it for like in this case, I'm waiting for 120 seconds. Thank you very much for your audience.
Cool. Thank you, everyone. Thank you, Prashant, for a really good demo. I'll just encourage you, if you want to know more about CODAIT and what we do and all the projects that we're involved in, CODAIT.org. Obviously follow on GitHub and Twitter. And if you're interested in the Model Asset Exchange, Spark on Cube, any of the topics, either come and speak to us afterwards. I don't know if we've got time for questions now. We might have time for one question. Yeah, I think just take it offline and in the hallway if you want to follow up on anything. Thanks very much.
Thanks, Nick.